Good evening, everyone. I hope you are all doing great and having a wonderful day. First of all, thank you so much for taking the time to join me for another webinar. Whether you're watching this live or catching the recording later, I'm really happy to have you here. Today, we are going to explore a technology that has been completely changing the way we think about manufacturing. It's a technology that allows us to create objects layer by layer directly from a digital design. Most people know it as 3D printing, but in manufacturing world, it is called additive manufacturing. Now, don't worry if you have never heard of it before or it sounds too technical. Throughout this webinar, I will explain everything in a simple way using everyday examples that anyone can understand. By the end of this session, you will know how 3D printing works, where it is used, its advantages, its limitations, and why industries around the world are investing so heavily on it. So get comfortable and let's begin our journey into the amazing world of additive manufacturing. So, from intricate medical devices to a big home, 3D printing is reshaping our worlds. So, when most people hear the term 3D printing, they often think of small plastic models or hobby projects. While that's certainly one of the applications, it represents only a tiny part of what this technology can achieve. Today, today additive manufacturing is transforming industries around the world. Engineers use it to manufacture lightweight aircraft components, surgeons rely on it for customized medical implants, automotive companies develop prototypes in days instead of weeks, and construction firms are successful printing entire buildings. Just a minute, small technical issue. Just wait for a second. Zoom it out, zoom it out. Not like that. First time. So let's continue. I'm sorry for the interruption. So, one of the greatest strengths of this technology is its versatility. It can produce everything from simple educational models to highly engineered components used in aerospace, healthcare, automotive, energy, and industrial manufacturing. What makes this more remarkable is that all the products are created using the same fundamental principle, that is, building an object layer by layer from a digital design. As we progress through this webinar, you will discover how this process works, why it offers significant advantages over traditional manufacturing methods, and why it is considered one of the most important manufacturing technologies in the modern era. Before we understand additive manufacturing, let's first understand the foundation of every product around us. So, what is manufacturing? Manufacturing is simply the process of converting raw materials into useful products. Almost everything we use in our daily lives has gone through some kind of manufacturing process. Take a simple plastic bottle an example. It didn't always look like this. It started as a raw plastic material, which was then processed, shaped, finished, and transformed into the bottle we use every day. The same is true for a wooden chair, a mobile phone, a car, or even the laptop you are watching this webinar on. Even one of these products began as a raw material and became useful through manufacturing. The goal of manufacturing isn't just to make a product, it's to produce the right product with the correct dimensions, good quality, and reliable performance. Without manufacturing, we wouldn't have vehicles, buildings, medical equipment, electronic devices, or household appliances. Manufacturing is one of the foundations of the modern life and plays a vital role in every industry around the world. Now, why is manufacturing important? Now that we understand what manufacturing is, let's take a moment to appreciate why it is so important. See, look around you. Almost everything you see today has been manufactured. The chair you are sitting on, the mobile phone in your hand, your laptop, your watch, your water bottle, even the light above your head, all of these started as raw materials before being transformed into useful products. But manufacturing is about much more than making products. It creates millions of jobs for engineers, technicians, machine operators, designers, quality inspectors, and many other professionals. It drives innovation by enabling companies to develop better products and new technologies. It also plays a major role in the country's economy by supporting industries, exports, and infrastructure. So, in short words or simple words, manufacturing improves the quality of our daily lives while powering economic and technological progress. That's why every developed nation invests heavily on manufacturing. So now let's see how these products have been traditionally manufactured over the years. Imagine you have a large block of metal and you want to make a machine component from it. Can we use the block directly? Of course not. First, you have to remove the unwanted material until only the required shape remains. This is exactly how traditional manufacturers work. So machines like lathes, milling machines, drilling machines, grinding machines use cutting tools to gradually remove the excess material. With every cut, the workpiece gets closer to its final shape. Like it's like a sculpture creating a statue from a stone block. The statue is already hidden inside the stone. The sculpture simply removes everything that doesn't belong. The traditional manufacturing follows the same principle. This method has been the backbone of industries for decades because it produces accurate, strong, and reliable components. In fact, most of the machine parts used in factories today are still manufactured using this conventional machining process. But while this approach is highly effective, it also has a few important challenges, and that's exactly what will explore next. Today, there are many manufacturing processes, but when we look at how a product is actually created, there are two fundamental approaches. The first one is what we have already discussed, traditional manufacturing. Here, we begin with a larger piece of material and gradually remove the unwanted portions using cutting tools until the final component is produced. And this is known as subtractive manufacturing. The second approach is the additive manufacturing, where instead of removing the material, this method builds the product by adding material layer by layer, exactly where it is needed. So both approaches have the same objective, to manufacture a finished product. The difference lies in how they achieve that goal. Traditional manufacturing or subtractive manufacturing has been the industry standard for decades and continues to be widely used. Additive manufacturing is a newer approach that offers unique advantages, especially when producing complex designs, prototypes, and customized components. So let's take a closer look at different types of manufacturing and why it is prevalent still. So, what is subtractive manufacturing? The before learning about the additive manufacturing, we first need to understand the traditional manufacturing method that has been used in industries for many decades, which is known as a subtractive manufacturing. The name itself gives us a clue. The word subtractive comes from the subtract. In the mathematics, we all learn addition, subtraction, everything. So comes from subtract, which means to remove. In this process, manufacturing begins with a larger piece of raw material called a workpiece. This process can be a metal block, a cylindrical rod, a flat plate, depending on the product being manufactured. The required shape is achieved by removing the unwanted material using cutting tools. As the cutting tool moves over the workpiece, small pieces of material are removed. These removed materials are called chips. The machining process continues until the component reaches its required size, shape, and dimensions. The subtractive manufacturing is one of the most widely used manufacturing methods because it provides excellent accuracy, high strength, and good surface finish. Even today, industries around the world rely on this method to manufacture a wide variety of machine components. Now, let's look at some of the most common examples of subtractive manufacturing. Although there are many machining processes used in industries, these four are the most widely used along with even the CNC machines. The first is turning. In this process, the workpiece rotates while the cutting tool removes the material to produce cylindrical components such as shaft or pins. Next is milling. Here, a rotating cutting tool removes material from a workpiece to create flat surfaces, slots, pockets, and various complex shapes. Milling is one of the most versatile machining operations and is widely used in CNC machining. The third process is drilling, which is used to produce holes of different sizes, which is the simplest and the most common machining operation. Then we have the grinding, where unlike the previous processes, grinding removes a very small amount of material using an abrasive wheel. It is mainly used to achieve high dimensional accuracy and smooth surface finish. Although these processes differ in how they remove material, they all follow the same fundamental principle. The final product is created by removing unwanted material from a larger workpiece. Now, subtractive manufacturing has been the backbone of modern manufacturing for decades. It's accurate, reliable, and capable of producing high quality components. However, like every manufacturing process, it also has certain limitations. One of the biggest challenges is material waste. Since the final component is created by removing material from a larger workpiece, the removed material becomes chips or scrap. In many cases, a considerable amount of original material is never part of a final product. Another challenge is the production of complex geometries. Components with intricate internal passages, lattice structures, or highly complex shapes can be difficult, expensive, or sometimes impossible to manufacture using conventional cutting tools. Manufacturing a single component may also require several machining operations such as turning, milling, drilling, grinding, etc. Each additional operation increases machining time, setup time, and production cost. Finally, many machine parts require additional finishing operations like polishing or grinding before they are ready for the use. These challenges encourage the engineers to rethink the manufacturing process itself and search for a completely different approach. So, now it's time to explore the technology that is transforming the manufacturing across the world: additive manufacturing. Unlike subtractive manufacturing, where unwanted material is removed from larger workpiece, additive manufacturing follows a completely different approach. Here, the product is created by adding material one thin layer at a time until the final shape is achieved. Like imagine you are building a brick wall. You don't start with a huge block and carve out a wall. Instead, you place one brick on top of another until the wall or building is complete. Additive manufacturing follows a very similar principle, except instead of bricks, the machine deposits extremely thin layers of material with high precision. The entire process begins with a digital 3D model created using a CAD software. The printer reads the design and builds. So, so what happens? The journey begins with a 3D model, which is created using a CAD software. The digital model represents the exact shape and dimensions of the product to be manufactured. Next, the model is processed using slicing software. The software divides the model into hundreds or even thousands of very thin horizontal layers. These layers become the printing instruction for the machine. The 3D printer then starts building the object from the bottom upwards. It creates one layer, then adds the next layer on top of it. This sequence continues until the complete object is formed. Finally, the individual layers bond together, bond together to create a strong, solid component that closely matches the original digital design. Although different technologies use different materials and energy sources, this layer by layer approach is the fundamental principle that defines it. Since material is added only, sorry, where it is needed, very little is wasted compared to many traditional manufacturing methods. Another major advantage is the ability to manufacture complex designs. Engineers can create lightweight structures, internal cooling channels, and intricate geometries that would be extremely difficult to produce using conventional machining. Additive manufacturing is also widely used for rapid prototyping. Instead of waiting days or weeks to manufacture a sample product, designers can often print a prototype within hours. Next is the flexibility. Designers are no longer limited by many of the constraints of traditional manufacturing. So, where are these 3D printing used? So, the application of additive manufacturing in aerospace industry, manufacturers use 3D printing to produce lightweight components that help improve the fuel efficiency. In the automotive industries, engineers rely on additive manufacturing to create prototypes, test new designs, and even manufacture specialized components for high performance vehicles. The medical field has seen some of the most exciting developments: customized dental aligners, hearing aids, prosthetic limbs, surgical guides, etc. In product design and prototyping, components can quickly transform a digital idea into physical model. Then in robotics, it is used where lightweight brackets, custom grippers, and specific specialized components can be manufactured efficiently. And did you know more than 95% of the custom hearing aids manufactured today are produced using additive manufacturing? While additive manufacturing offers many impressive advantages, it is important to remember that no manufacturing process is perfect. One of the biggest challenges is the high cost of equipment. Industrial 3D printers, especially used for metal printing, can be very expensive compared to conventional machines. Another limitation is the production speed. Since objects are built one layer at a time, manufacturing large quantities of identical products can take much longer than traditional mass production methods. Material availability is another consideration. Although the range of printable material is growing every year, it is still more limited than the wide variety of materials available for conventional manufacturing. Many printed components also require post processing. Depending on the technology, the part may need support removal, cleaning, heat treatment, machining, or polishing before it is ready to use. Finally, operating industrial additive manufacturing system requires trained personnel who understand the machine settings, materials, software, and post-processing techniques. So, for this reason, industries often use both traditional and additive manufacturing together, selecting the best process based on the product, material, quantity, and applications. So we know that additive manufacturing builds object layer by layer. But one important question remains: do all 3D printers work in the exactly same way? The answer is no. Just as different manufacturing machines are designed for different jobs, additive manufacturing also includes several different technologies. Each technology uses a different material and different method to build the object. Some printers melt plastic filament, while others cure liquid resin using UV light. Some technology use fine powder that is fused using a laser, and advanced industrial systems can even manufacture fully functional metal components. Each technology has its own strengths, limitations, cost, accuracy, and applications. Choosing the right technology depends on the type of product being manufactured and the material properties are required. In this webinar, we'll be looking at the four most important technologies used in the industry, known as the FDM, SLA, SLS, and metal 3D printing, or the DMLS bar SLM. By understanding these technologies, you will get a clear picture of how versatile additive manufacturing has become across different industries. So let's begin with the most popular and widely used 3D printing technology, the fused deposition modeling, or simply FDM. Here, a filament, this process starts with a plastic filament, which is supplied on a spool. This filament is fed into the heated nozzle where it melts into the semi-liquid state. The printer then moves the nozzle according to the digital design, depositing the molten plastic very precisely onto the build platform. Once the first layer is complete, the build platform or print bed moves slightly, allowing the next layer to be deposited. This continues until the entire object is built. FDM is popular because it is simple, affordable, and easy to operate. It is widely used for concept models, functional prototypes, educational products, and low volume productions. Some of the most common materials used here are PLA, ABS, and PETG, each offering different mechanical properties depending on the application. Next is the SLA or stereolithography, getting the high precision with the liquid resin. Unlike FDM, SLA does not use plastic filament. Instead, it uses a special liquid material called the photopolymer resin. Inside the printer is a tank filled with this liquid resin. A UV laser or a UV light selectively cues or hardens the resin exactly where the part needs to be formed. Once one layer is complete, the build platform moves slightly, allowing the printer to create the next layer. This process continues until the entire object is complete. One of the best advantages of SLA is its outstanding accuracy and smooth surface finish. So, because of this, SLA is widely used for applications such as where fine details are important, like jewelry. So, industries commonly use SLA to manufacture dental models, jewelry patterns, engineering prototypes, etc. So compared to FDM, SLA generally produces smoother parts with finer details. However, the resin materials require careful handling and the printed parts usually needs washing and UV post curing before they are ready for use. So before we start learning the different 3D printing technologies, these are some actual components produced using additive manufacturing. These are the real part manufactured using FDM and SLA technologies. As you watch the video, so just understand the gray ones are made using SLA and the other colored ones are made using FDM. Next is the selective laser sintering or the SLS. Unlike FDM, which uses plastic filament, and SLA, which uses liquid resins, SLS uses a fine polymer powder as the raw material. The printing process begins by spreading a very thin layer of powder across the build platform. A high powered laser then scans only the areas that need to become the part of the component. The heat from the laser fuses the powder particles together, creating one solid layer. Once the layer is complete, the build platform moves down slightly. Another thin layer of powder is spread, and the laser repeats the process. Layer by layer, the final component is built. One unique advantage of SLS is that the surrounding loose powder naturally supports the part during printing. This means separate support structures are often unnecessary, make it possible to manufacture complex shapes more easily. So, because of its strength and design flexibility, SLS is widely used for functional prototypes, engineering components, customized products, and low volume production across many industries. And the unused powder can often be collected, processed, and reused for a future print jobs, helping to reduce the material waste. Next, till now we have learned about plastics, liquid resin, and polymer powder. But what if we need to manufacture a strong metal component? That is where metal 3D printer comes. The two most common industrial technologies are DMLS or the direct metal laser sintering or the selective laser melting, that is SLM. Both processes use a fine layer of metal powder spread across a build platform. Here also, a high power laser then scans the required areas and melts and fuses the metal powder according to the digital design. Once each layer is completed, the platform lowers and a fresh layer of powder is spread and the process repeats until the entire component is built. Metal 3D printing makes it possible to manufacture lightweight yet strong parts with highly complex internal features that are extremely difficult to produce using conventional machining. So, because of these capabilities, industries such as aerospace, medical, automotive, and energy increasingly use metal additive manufacturing for specialized components where performance and precision are critical. Although these machines are expensive and require controlled operation condition, they have opened new possibilities in modern engineering and product design. For example, aircraft engineering manufacturers use metal 3D printing to produce lightweight fuel nozzles and complex turbine components that improve efficiency and reduce weight. So, one of the biggest strengths of the additive manufacturing is the wide variety of materials that can be used. The choice of material depends on printing technology, the application, and the required mechanical components. For desktop FDM printers, the most common materials are PLA, ABS, PETG, nylon, TPU. For SLA printers, we have liquid polymer resins which produce smooth furnitures. They are for dental models, jewelry, or precision prototypes. We have standard resin, we have flexible, castable, all those resins. SLS technology uses polymer powders, and for metals, we use required materials. And then we have composite materials, which are carbon fiber, glass fiber, etc., which are also used for 3D printing. In metal 3D printing, the most widely used material is titanium because it is both lightweight and exceptionally strong. So, additive manufacturing is no longer just an emerging technology, it is rapidly becoming an important part of modern manufacturing across the world. As machines become faster, materials become stronger, and software becomes smarter. The capabilities of 3D printing continue to expand. Industries are moving towards smart manufacturing, where digital design, automation, artificial intelligence, and additive manufacturing work together to create highly efficient production systems. Another exciting trend is the personalization. Instead of producing identical products for everyone, manufacturers can now create customized product specifically for an individual. So these are already available in case of jewelries, dental aligners, hearing aids, prosthetic limbs, etc. Then large scale construction is another rapidly growing field. Even space agencies are exploring additive manufacturing to produce tools, spare parts, and future habitats during long duration space missions. Like as NASA and other space agencies are researching on 3D printing technology that could manufacture tools and replacement parts directly in the space, reducing the need to carry large inventories on future missions. So before we conclude, let's take a moment to revisit the key concepts we covered today. We started by understanding what manufacturing is and why it plays such an important role in our daily life. We then explored traditional manufacturing, where products are created by removing metal using machining process. Next, we introduced additive manufacturing, a completely different approach where objects are built by adding material layers by layer. We compared additive and subtractive manufacturing, understood how the printing process works, and learned the importance of layer by layer manufacturing. We also explored major 3D printing technologies, including FDM, SLA, SLS, and metal 3D printing, along with the different materials they use and the industries where they are applied. Finally, we looked at the advantages, limitations, and the exciting future of additive manufacturing. So, I hope this webinar has given you a clear understanding of how the technology is transforming manufacturing and why it is becoming an essential part of modern engineering. Whether you're a student, professional, or simply curious about technology, this is a field that is only going to grow in the years ahead. We have now reached the end of today's webinar. Thank you so much for joining me and spending your valuable time in learning about additive manufacturing. I truly hope this session has given you a better understanding of how this exciting technology is transforming the manufacturing industry. If today's webinar has inspired you to build a career in CNC machining and manufacturing, I'm happy to let you know that the enrollments for batch 7 of our 45 day CNC Operator Come program course has now started. This is a comprehensive industry oriented training program designed to help students and professionals develop practical skills that are required in today's manufacturing sector. Seats for the upcoming batches are limited and only a few are still available. If you're interested in joining or would like to know more about the course structure, eligibility, or admission process, please feel free to contact us. I would also like to invite you to continue learning with us through the free technical webinar series conducted every Saturday. Every week, we explore new topics related to CNC machining, CAD CAM, metrology, engineering drawing, manufacturing technologies, industrial automations, and many more practical subjects. If you enjoyed this session, please don't forget to subscribe our channel and enable notifications so you never miss an upcoming webinar. Once again, thank you for your time, your support, and your enthusiasm for learning. This is Pia Sharat Nambia, Technical Trainer, signing off. Until we meet again, keep learning, keep innovating, and keep building the future. Thank you and have a wonderful day. Thank you.